In relativity, proper time along a timelike world line is defined as the time as measured by a clock following that line. It is thus independent of coordinates, and a Lorentz scalar. The proper time interval between two events on a world line is the change in proper time. This is the quantity of interest, since proper time itself is fixed only up to an arbitrary additive constant, namely the setting of the clock at some event along the world line. The proper time between two events depends not only on the events but also the world line connecting them, and hence on the motion of the clock between the events. It is expressed as an integral over the world line. An accelerated clock will measure a smaller elapsed time between two events than that measured by a non-accelerated clock between the same two events. The twin paradox is an example of this effect. In terms of four-dimensional spacetime, proper time is analogous to arc length in three-dimensional space. By convention, proper time is usually represented by the Greek letter tau to distinguish it from coordinate time represented by t. By contrast, coordinate time is the time between two events is measured by an observer using that observer's own method of assigning a time to an event. In the special case of an inertial observer in special relativity, the time is measured using the observer's clock and the observer's definition of simultaneity. The concept of proper time was introduced by Hermann Minkowski in 1908, and is a feature of Minkowski diagrams. Mathematical formalism. The formal definition of proper time involves describing the path through space-time that represents a clock, observer, or test particle, and the metric structure of that space-time. Proper time is the pseudo-Riemannian arc length of world lines in four-dimensional space-time. From the mathematical point of view, coordinate time is assumed to be predefined and we require an expression for proper time as a function of coordinate time. From the experimental point of view, proper time is what is measured experimentally, and then coordinate time is calculated from the proper time of some inertial clocks. Proper time can only be defined for timelike paths through space-time which allow for the construction of an accompanying set of physical rulers and clocks. The same formalism for space-like paths leads to a measurement of proper distance rather than proper time. For light-like paths, there exists no concept of proper time and it is undefined as the space-time interval is identically zero. Instead, an arbitrary and physically irrelevant affine parameter unrelated to time must be introduced. In special relativity, let the Minkowski metric be defined by and defined for arbitrary Lorentz frames. Consider an infinitesimal interval expressed in any Lorentz frame and here assumed timelike, separating points on a trajectory of a particle. The same interval can be expressed in coordinates such that at each moment, the particle is at rest. Such a frame is called an instantaneous rest frame. Due to the invariance of the interval, one may write, since in the instantaneous rest frame, the particle is at rest. Since the interval is assumed timelike, one may take the square root of the above expression, or given this differential expression for tau. The proper time interval is defined as here p is the world linear from some initial event to some final event with the ordering of the events fixed by the requirement that the final event occurs later according to the clock than the initial event. Using and again the invariance of the interval, one may write where v is the coordinate speed at coordinate time t, and x, y, and z as space coordinates. It should be noted that the first expression is manifestly Lorentz invariant. They are all Lorentz invariant, since proper time and proper time intervals are coordinate independent by definition. If d, x, y, z are parameterized by a parameter lambda, this can be written as if the motion is of the particle is constant. The expression simplifies to where delta means the change in coordinates between the initial and final events. The definition in special relativity generalizes straightforwardly to general relativity as follows below. In general relativity, proper time is defined in general relativity as follows. Given a pseudo-Riemannian manifold with a local coordinates x mu and equipped with a metric tensor g mu nu, the proper time interval delta tau between two events along a timelike path p is given by the line integral. This expression is, as it should be, invariant under coordinate changes. It reduces to the expression of special relativity in flat spacetime, in the same way that coordinates can be chosen such that x1, x2, x3 equals constant special relativity. This can be done in general relativity too. Then, in these coordinates, this expression generalizes definition and can be taken as the definition. Then using invariance of the interval, equation follows from it in the same way follows from, except that here arbitrary coordinate changes are allowed. Examples in special relativity. Example 1. The twin paradox. For a twin paradox scenario, let there be an observer A who moves between the coordinates and inertially. This means that A stays at for 10 years of coordinate time. The proper time interval for A is then, so we find that being at rest in a special relativity coordinate system means that proper time and coordinate time are the same. Let there now be another observer B who travels in the x direction for 5 years of coordinate time at 0.866 c2. Once there, B accelerates, and travels in the other spatial direction for another 5 years of coordinate time 2. For each leg of the trip, the proper time interval is so, the total proper time for observer B to go from to is 5 years. Thus, it is shown that the proper time equation incorporates the time dilation effect. In fact, for an object in a linear spacetime traveling with a velocity of v for a time, the proper time interval experienced is which is the linear time dilation formula. Example 2. The rotating disk. An observer rotating around another inertial observer is in an accelerated frame of reference. For such an observer, the incremental is that in GR1 can use any metric which is a solution of the Einstein field equations, not just the Minkowski metric. Because inertial motion in curved spacetimes lacks the simple expression it has in linear, the line integral form of the proper time equation must always be used. Example 3. The rotating disk. An appropriate coordinate conversion done against the Minkowski metric creates coordinates where an object on a rotating disk stays in the same spatial coordinate position. The new coordinates are and the t and z coordinates remain unchanged. In this new coordinate system, the incremental proper time equation is with r, theta, and z being constant over time. This simplifies to which is the same as in example 2. Now let there be an object off of the rotating disk and at inertial rest with respect to the center of the disk and at a distance of r from it. This object has a coordinate motion described by d theta equals omega dt, which describes the inertially at rest object of counter-rotating in the view of the rotating observer. Now the proper time equation becomes so for the inertial at rest observer. Coordinate time and proper time are once again found to pass at the same rate, as expected and required for the internal self-consistency of relativity theory. Example 4. The Schwarzschild solution. Time on the Earth. The Schwarzschild solution has an incremental proper time equation of where t is time as calibrated, with a clock distant from an at inertial rest with respect to the Earth. R is a radial coordinate, is a colatitudinal coordinate, the angular separation from the North Pole in radians. Theta is a longitudinal coordinate, analogous to the longitude on the Earth's surface but independent of the Earth's rotation. This is also given in radians. M is the geometrized mass of the Earth, m equals gm, c2, m is the mass of the Earth, g is the gravitational constant. To demonstrate the use of the proper time relationship, several sub-examples involving the Earth will be used here. For the Earth, m equals 5.9742 times 1024 kilograms, meaning that m equals 4.4354 times 10⁻³ meters. when standing on the North Pole, we can assume. In this case, the Schwarzschild solution proper time equation becomes, then using the polar radius of the Earth as the radial coordinate, we find that at the equator, the radius of the Earth is r equals 6,378,137 meters. In addition, the rotation of the Earth needs to be taken into account. This imparts on an observer an angular velocity of 2 pi divided by the sidereal period of the Earth's rotation, 86,162.4 seconds. So, the proper time equation then produces this should have been the same as the previous result. But as noted above, the Earth is not spherical as assumed by the Schwarzschild solution. Even so, this demonstrates how the proper time equation is used.